I guess I'm ready. So let's start. Yeah, hi everyone. I'm Minna Haikonen and welcome to this month's weather briefing, also from behalf of me. Very, very cloudy day here in Finland. I hope most of Europe is bathing with sun. But let's see how today's weather situation looks a little bit more. So I'm going to talk a little bit about present weather situation in Europe, maybe focus a little bit on convection, because after my speech, Paavo is going to give you a really interesting presentation about severe thunderstorm Kiira that happened here in Scandinavia last August, 12th of August 2017. So first of all, I would like you to please mark on the map where your locations are, where you are participating from to this session. So whether you are forecaster, researcher, manager, trainer, or if you have some other meteorological interests, why you are participating to this weather briefing. I guess you can use your pointer, as Marco said, to point out your name on the right box. So we have quite many forecasters and actually quite many other members. So it would be quite nice to know what your other interests are, but maybe we can talk about that later after the presentation. But it's nice to see that we have many participants from all around Europe. I guess northern parts of Europe is a little bit quieter, but otherwise we have quite nice selection of people from all around the Europe. Let's proceed. Next slide. So what is going on today? Here is today's air mass RGB image from 6 UTC, and now I would like you to look at the picture and show where are the warm air masses and cold air masses, and you can do that maybe by drawing little dots with blue or red on the areas that you can identify the warm and blue air masses. Yeah, you don't have to maybe draw any big lines, but just maybe little dots there and there where you can see the warm air masses. Yes, I can see really good, nice dots all around and there, yeah. I didn't come up with any better idea how to spot the areas, but I think this works just fine, so thank you. It's true that we have really cold air masses here, and also you spotted the area around here where we have colder air masses, and it's quite obvious that here in the south we have the warm and moist air masses, and of course the large frontal area here, and here can be seen really well from the image. Now I just like to erase everything, but I guess I need to first stop annotation. Yes, now we have everything clear again. And also I would like you to point out the dry and sinking air masses where we can actually see the ongoing cyclogenesis at the moment and the dynamically active areas. So now you have the right to make again some drawings. Yes. And just for the reminder, dry air masses are characterized by the reddish color in the air mass RGB, and this is result from a combination of low tropopause level and high ozone concentration in the level of highest instrument sensitivity in combination with strong radiances in both water vapor channels. So this is just a reminder of how to analyze this image. And actually in warm air masses, the red and orange areas depict dry and hot air. Yes, I guess you have spotted all the areas. Actually, this area, in my opinion, is rather dynamically passive area, although we can see the red stripe here. Yeah, let's proceed to the next slide. And here I have the ECMWF 850 hectopascal temperature. So we can see from the model data that actually the really cold air masses are right here, really north, and here, as you spotted on the western side of the UK, we can see some colder air mass also here. But at the same time, we have really warm air masses on the eastern parts of Europe and in the Mediterranean area south here. So next I wanted to show you the water vapor image, and you can spot the upper level lows from this picture, and maybe you can draw little M's on the spots that we have the upper level lows at the moment. And also at the same time, you can spot also the jet streams. And I am about to give you the answers in a few minutes when you have gotten your remarks on the picture. I guess in this situation, the upper level lows are quite well standing out and quite nicely and easily spotted from the image. Okay, thank you very much. Now I clear all your answers again, so we can proceed to the same water vapor image with the 500 hectopascal geopotential height. And as you spotted, we have quite many upper level lows at the moment, and one really large ridge in the eastern parts of Europe, and another in the northern parts of Europe. And in the next slide, I have again the air mass image with the 300 hectopascal wind speeds with jets. So as you marked, we have really strong jets going on here in the North Atlantic, and or otherwise the jets are situated on a really wavy formation, so it's quite interesting that the jets are going up and down like this. Here we have another jet, and yet another one here circling around Italy, going up again north and going down again here in the eastern parts of Europe. So from this picture and with this knowledge that we have from these earlier images, now we know where are the dynamically interesting areas, and we know where the jets are. So can you spot any interesting convective areas at the moment that maybe we should have a little bit closer look at? You just can draw maybe circles in the picture where you can spot some interesting areas that you might want to have a look. I hope that the areas will be the similar that I had in mind. Yes. Yeah, I agree with many of you. Thank you very much. Now I'm again going to stop the annotating and move on to the next slide, because first of all, when I looked at these pictures, I thought that there are actually interesting areas especially in the southern parts of Europe. And when I looked at the meteor alarm warnings and where might be heavy precipitation or thunder, so I spotted that actually in Italy there are many warnings about thunder, and in Slovenia and in parts of Austria, for example. So I decided that maybe we could have a little bit closer look at these areas. I took a model sounding from EUMWF from Italy, from central parts of Italy. 12 UTC, we have one too many numbers here, but don't mind it. Well, actually from the model sounding here, we can see that we have moderate CAPE around 400 joules, and then we have a convective inhibition actually around 0. And if we look the wind shear that we actually saw from the picture earlier with the, I'm going to show you again this area here, that we really have some convective phenomena going on at the early stage 6 UTC, but the jet is going around this area. So as we see from the model sounding here, we really don't have any wind shear. So in my opinion, we might think that there will be some single cell thunderstorms forming up later on during the day. And then another model sounding that I took was from Slovenia. There we found Cape from 400 to actually 1000 joules, and this is somewhere central parts in Slovenia. And again, we don't have really that much convective inhibition, but when we look at the wind shear, we really have something going on because the wind shear is 15 meters per second. In the lower levels, we don't have that much wind shear. We have actually quite weak winds in the lowest 1 kilometer, but we might suspect that we might have some multi-cell thunderstorm formation later on during this afternoon, and it's really interesting to see how the situation looks now. But again, I'm going to go a little bit back. Why I decided that the area here around Slovenia and eastern parts of Austria and actually in Croatia, the situation is quite interesting because there's the frontal zone front that has just passed the area, and we have the left exit of the jet right here, and some moist and warm air. And as we look at the picture here, where we have the 500 hectopascal geopotential heights, the upper lows are situated here over Italy, but we might have some slight upper throw area here where we have the left exit of the jet. So this is what the situation looked half an hour ago. We had the day natural color RGB and convective storm RGB from 12 UTC, and we can see some convective cells here in southern Italy, and quite a lot of cloudiness still in these areas, but where we have a little bit more clear skies, we can see some convective activity right now starting on. And if we look at the convective storms RGB, we can spot the same areas a little bit better with the red areas that are marked here. So it's quite good image to look when we have convective storms forecasted. So something is definitely going on today, but as we speak, the time is running, and I want to let Paavo present his presentation. So I wish you good luck with forecasting convective phenomena, and I'll let Paavo continue from here. Thank you.
Okay, hello, this is Paavo speaking. I'm a forecaster in FMI, our Safety Weather Center. Yes, that's the name. And I will put my PowerPoint on. I hope you will all see it. Actually, I don't have very much time anymore, but I'm going to maybe speed a little bit this presentation, but I will go anyway to the end of it. Let's start. So we had very powerful thunderstorm, severe thunderstorm during last August, 12th August, and it actually did some damage, actually quite much. So weather-related tasks for civil protection, electricity outages, forest damage, and very strong wind gusts, even 33 meters per second. And several outdoor events were interrupted by this storm. So I will go through some forecasting with numerical weather prediction models, and then towards nowcasting stage, where we look more at the satellite images also. And one method that I used in this case study is in this ingredients-based forecasting. So let's go forward. Maybe I mentioned this also, that this ingredients-based forecasting is really good tool to keep this one step ahead of the weather situation. So it's very good. Okay, these are good questions that actually leads to reasonable forecast. Step one is to ask ourselves that will there be any thunderstorms? So what is the availability of moisture, instability, and lift? And if the thunderstorms will develop, will they organize, and how will they organize? Will there be single cells, multi-cells, supercells, or larger systems like MCSs? What is the mode of convective situation? And then what is the propagation of these convective cells or MCSs? And what is the most probable evolution of this MCS if it forms? So when it will be increasing in strength, and when is the mature stage and weakening stage, and why? So based on these questions, we should assume or assess the main hazards and warning areas also. Okay, let's go into the case. So this is in the left-hand side, you see 850 millibar temperatures, and also 850 millibar geopotential height. And in the right-hand side, you see 500 hectopascal geopotential and relative topography. So you see this very warm air mass flowing towards Finland. Actually, very warm air mass concerning taking into account the time of the year. So this is very warm air mass in this time of year for us. And then you see this upper level low here approaching from the left, providing some lifting, large scale lifting also. And of course, from these images, you can assume that there is some kind of frontal system coming from west. So now we have to take into account these ingredients. So we should probably look out the moisture, then instability, and is there enough lifting present that there actually will be something happening. And where these kind of ingredients overlap, there we might expect thunderstorms. And there, then also with the red circle you see here, the wind shear, which is kind of fourth ingredient for developing strong thunderstorms. Okay. So I have an image of this skew teeth sounding diagram. We go through the necessary ingredients also from here. So instability, you need to have temperature decreasing enough with height. Then moisture. In this case, this is actually a sounding from Estonia somewhere. I don't remember the exact place, but it's not important. So you can see regarding the moisture, it's very thick, and there's actually like 15 grams per kilogram mixing ratios there. So very much moisture. And then we need to assess the possibility for lifting. And in this case, you can actually see that we have convective inhibition. It's quite much actually, and very much CAPE, also over 2000 joules per kilogram. So we expect if there will be thunderstorms, they will be very powerful, very intense. But the question is, where will they actually initiate, or will they? So we go through some numerical weather prediction charts here. So in the first picture on the left, you see actually combination of different things. There are 300 hectopascal heights with the blue lines, and then there are instability plus moisture in the form of CAPE here, showed in the shadings, and the yellow color depicts over 1000 joules per kilogram, and the orange is 2000. Okay, and then we see also the deep layers here with vectors shown in the map. So actually we can see that there's quite a lot of wind shear there present and overlapping with the area of CAPE. So the wind shear actually tells us something about the organization of the thunderstorms. And then in the middle image, we see the source of lift. In this case, it's actually depicting the fronts, weather fronts. So there are theta E from 850 millibar level, and the gradient of theta E in the same level, and then a mean sea level pressure also. So we actually see quite nice tongue of moist air here towards Finland, coming towards Finland, and then this frontal system, like cold front coming from the west at the same time. So we suppose that this will be enough lifting for the initiation of thunderstorms. And the right-hand side image, we actually have plotted some vectors on there over most unstable CAPE shading. And these vectors actually depict the mean steering flow. So it's a mean flow vector from LCL level to around 6 kilometers height. So we expect if something happens there and initiates, we expect to have pretty fast-moving convective cells there. Of course, we should look more in detail these different ingredients like moisture. So here's just the lowest 500 meters mixing ratio. So we see very much moisture there. Okay, let's go forward. So then we have to ask that what is the evolution of the MCS like? Because in this situation when we have frontal forcing and we have a lot of energy, we have all these ingredients in place, so we really expect to have multi-cell storms and maybe MCS forming, and we should ask ourselves that what is the evolution? So then we should ask what is the most probable place, and this time we can say that it will likely be the cold front, and the movement in relation to favorable environment. Yes, we will see in some time, we will go there. And then time spent in the favorable environment, that relates to the intensifying of the storm. So the more time it has, then the more it will intensify. And yes, changes in the environment and possible reasons for dissipation, we go into these things. Okay, so now we go to nowcasting stage. So the importance of numerical weather prediction models compared to all of these observations and observation information sources will decrease. and the observations will increase in the importance. So this is an analysis from 6 UTC this day that we had the thunderstorm, and this shows very moist air blowing towards northwest, towards this cold front actually. And we have dew points from the observations there with the blue numbers, and there are very, very moist air there. So the dew points are around 20 degrees almost. So let's go forward. This actually is very good RGB satellite product that depicts quite nicely even the low-level moisture. This is, let me see the name, it's RGB 24-hour ash microphysics channel. So actually this, I hope you see the arrow because I'm pointing over the map. So Finland is somewhere here, Lake Ladoga is here, and this bluish area depicts very moist air. And this area here is much more drier, also here, much more drier. So this blue area correlates well with moisture. Okay, then we have something happening around 11 UTC. The long cold front is, as you remember, it's around here. So we have an onset of deep moist convection there. Because in the warm sector, we had very much of convective inhibition, so there we have nothing actually going on. So it's all in the along the cold front. And this is to show you the power of meteorological workstation in nowcasting. So we have plotted there the trajectories from 500 millibar level and 700 millibar level, which actually are good approximation of the average steering flow of deep convective clouds. And they are really showing the direction towards actually Helsinki area, so it's our capital city area, and so this is good tool. And actually, when this initiation started along the cold front, we could almost already then see that it will actually move in this direction. But we should be aware of this using of these trajectories, however, because they might deviate greatly from the mean steering flow. I mean, the movement of real MCSs can deviate from this steering flow quite much. But in some cases, it's very good approximation. And you see this black dotted dots there over the trajectories and satellite image, which actually is the forecast. How should this cloud move forward? And we can see even in this stage that the thunderstorms actually are moving a bit faster than the approximation of the steering flow. Okay, then in this time it's actually 13 UTC. We have very rapid development and intensification based on the anvil growth rate in the last images, and it really shows signs of faster movement than the steering flow indicates. And this is again one analysis from 12 UTC. We see that dew points are very high, 22 degrees even in the most moist areas, extending towards southern Finland even. And there's some prefrontal convergence zone here also, and the deep convection going on with the cold front there. Okay, and this is again the satellite image, which really nicely shows also the moist areas and the gradients in the moisture there. Okay. And 13 UTC, we calculated new trajectories that indicate straight hit to western and northwestern Estonia and even Helsinki. And this developing MCS begin also show signs of cold pool domination, which actually meant that it was moving faster than the steering law indicated. And in the image are plotted also these Corfidi vectors, downwind vectors, which indicated also propagation speeds of 100 kilometers per hour. So actually the storm was moving almost that fast already in that stage. And there are some NWP fields also plotted there. The shadings indicate the cape from ECMWF. So it looks like the path of the MCS that is forming there really seems favorable for further intensification during the next hours. And that's what actually happened. And the ECMWF model showed there actually precipitation over this green rasterized area, and there's actually nothing happening there. So we should have these alarm bells ringing in our heads that something is wrong there. And we actually see from the observations we see that the temperatures over that area are even 7 degrees higher than in the model. So we assume that there are a lot of more cape than this map indicates in reality. Okay, and the temperatures are over almost 30 degrees, and the dew points are 21 degrees. So also the observations indicates very good environment for intensification of the system. And when we go forward, we can see actually the intensification in the satellite image, and also other areas in the Baltic states. In this time, we should notice when we are nowcasting that this moist tongue here with these observations with high dew points, it's really narrow, and this system is moving very fast. So it will eventually end up in the area that is not so good for the convection. So it's less favorable air mass. So we expect weakening and even dissipation in a couple of hours if this rapid movement or propagation will continue on. And this is the time when the system hit Helsinki area and also many other parts of Baltic states. And here is these Corfidi vectors plotted there on the map. So in the upper side of the image, we see very rapid those vectors that indicate very rapid movement, and in the lower parts of the image we see this upwind Corfidi vectors, which actually indicates very slow movement, and that is what actually happened there. So in this case, the Corfidi vectors were very good estimating these speeds. If we can just pick that which vector we should believe, that's always a very difficult job to do. I suggest you reading this paper about Corfidi vectors. So maybe you can watch this presentation again later and then take this information if you want to read this paper. And how did the models actually perform regarding the precipitation? So these are satellite images, of course, there, and we have 6 different models with blue raster areas with over 0.5 millimeters per hour rain. So actually the models were very poor in this situation. And only model that actually did get something useful the day before was ECMWF. It really got some rain in this area. Okay, and this is the radar image. I'm almost in the end of the presentation, so hang on. The left-hand picture shows also the lightning over the radar image, and the right-hand side image is without lightning. So we really see this bow echo type of formation here, straight hit to Helsinki, and the worst, it was very rapid moving feature, so it really lasted just about 5 to 10 minutes. I mean the worst part of it. And intense rain, like 10 millimeters per 10 to 15 minutes, and the visibility got very poor for a moment. And these are the measured wind gusts from this Helsinki area and from this MCS. And the reddish areas in the image over here shows actually the density of emergency calls that came in. So very powerful system. And this is the whole Kiira's life cycle. So it really is nice looking development there. And this is my last slide actually. Now we could take in some questions if you like.